Yeah, but every time we go into that Starbucks, there's like a line out the door because my appointments with them are like at 8 a.m. So I can get back here for like a 10 o'clock or 11 o'clock class. Usually it's 10 o'clock class. And so, we're walking in and we just go right up to get our coffee because we've done the pre-order thing. And we got people screaming at us like you. They probably just screamed at you because they figured that since you're foreign, you didn't know what you were doing. We're going to start talking about cues today. And he's like, he must not know how cues work. He's going to go talk to Dr. Manoj. How many of you get that joke? Nobody gets the joke? Who has had Dr. Manoj? Okay. He's British, right?
Yeah.
The Brits are famous for queuing up. They don't say get in line, they queue. Yeah, Brits will create queues anywhere. So ask him for queuing tips next time you see him, and he'll give you a whole rundown. Okay, breakdown for the exam. And this was after I'd already put any extra credit in, so these numbers might be slightly skewed. Low grade was a 53. Max grade was a 104. Average was an 83. Now, while not everybody did as well as I maybe would have expected them to do as individuals, as a class, you did pretty well. I would say, and even some of the individual scores that were a little lower, it was due to like a singular misunderstanding that haunted you through the exam. So I think those are all remediable. Is that a word? Fixable. Those are fixable things. Okay. So I think everybody is in okay shape. I don't think I actually reached out to anybody and said you need to bail. So usually I would have done that by now. So some of the grades I'm sure aren't as high as you wanted them to be, but I think everybody is doing all right. So that was positive. Because I don't think this was like an overly simple exam. I don't think it was overly crazy hard, but it was a fair assessment exam, I think. Did anybody think it was too hard? Did anybody think it was too easy? Yeah, I felt like I kind of I felt pretty good about it. Sometimes my exams are too hard, but so, and as a class, you guys did pretty well, so I was impressed. So a couple grades over 100, that was after the curve, or after the, some extra credit points. So, there were 6 people out of 15 who were above a 90 on the exam, which is, that's good. I'm happy with that. It's almost half the class. And then, some 80s, couple 80s, 4 70-somethings. And truth be told, a couple of those people would have been at an 80 if they had just done some of the extra credit opportunity stuff. The 60s, those were, that's, a little bit borderline, but at least one of those people had that one of those, misunderstandings throughout the entire exam that cost them like 5 points per question type thing. The 50-something is kind of suspect. So, that's probably, you need to start out, be able to apply some of your stuff you're learning from the homework to the exam a little bit better. But as a whole, I thought the class did all right. All right, so let's go over the exam. I'll just talk about some of them and then we'll write some of them. So why are arrays considered to be fast and linked lists considered to be slow? So I was looking for something dealing with, contiguous memory. So arrays are implemented in terms of a contiguous memory. So that's memory in a row. So you can, to move to a specific bucket of an array, you can calculate the exact memory location of that guy. Something along those lines, whereas linked lists do not exist in contiguous memory, and therefore to get to a certain bucket you have to traverse the entire list from the beginning, or if you happen to have a tail you can go from the end, but whatever, you had to traverse the list to get to your final destination. So in terms of performance, linked lists are relatively slow, arrays are relatively fast, but on the flip side of it, I didn't ask about memory efficiency, did I? No. But on the flip side, arrays are memory inefficient for the exact same reason. Right? Or linked lists are memory efficient for the exact same reason. So it's kind of a trade-off thing there. What are the three methods that a stack must support, and what does each one do? So we have push, pop, peek. Now, officially in data structure world, peek is not a required method for stacks, but I teach it as one. I mean, you got to have peek. It's the thing. So what does push do? Push adds something to the top of the stack. And a stack is the last in, first out queue, right? So the last thing you put on would be the first thing that comes off. So push puts something onto the stack on the top. Pop removes the top of the stack and returns it. Peek shows the top of the stack but does not remove it. Okay, it gets you the top of the stack but without actually removing it from the stack. Does that make sense? All right, and understanding those three things was a necessity for number 9 when you went to read that code. And we'll get down to that here in a few minutes. Number 3, how much space in memory does a 20 bucket int array take? Integers in Java are 32-bit. So 20 of those is 640 bits. You could also look at an int as being 4 bytes, which is equal to 32 bits, because 4 times 8 is 32. So with that in mind, 80 bytes is equivalent, right? Now, some people I gave most of the credit to if you did the right math but started with the wrong int size. So, if you said, oh, well, ints are 64 bits and you did the math based on that, I maybe took off a point or two or something like that. So as long as your math kind of made sense, that you understood that you have 20 of these guys and each one of them needs to be this size. And then you had some really funny made up numbers. I think it was like a 1.536 e to the negative 4. Was that it? Yeah. Did I get that right? Did I say that? E to the 525. 525. E to the negative 6 or 4? 4. Yeah. Yeah. That's wrong. That is an incorrect answer. Other incorrect answers would be like 20, stuff like that, where you didn't really show that you understood that there's a size to an int, and that translates into the full size of the array. So that's when that one's really related to question number 1 about the amount of contiguous memory an array might take up. Make sense? Okay. And for the most part, 1, 2, and 3 were most people got those at least mostly right. 3 you had some good math, wrong base size of an int going on, which I wasn't going to kill you for, but right at error-free hello world program, most people got that right. A couple people forgot to do the public class thing. I don't remember if I might have hit you for 1 or something like that, but so I showed mercy. But remember, a program is the whole kit and caboodle. Okay, public class, whatever, public static void main, string array args, blah blah blah, all that stuff. Okay, just the hello world method for main would be just the main part. Let's see. Okay, so the next questions, we're assuming there's a stack and a linked list object that are capable of holding integers. And you can make any reasonable assumption regarding the methods that each of these data structures already have. That is, you can't just assume they already have the method I'm asking you to write. It's built into it. All right, so number 5, write a recursive method that takes a stack and it prints to the screen the contents of the stack. You do not have to preserve the contents of the stack. All right, so first of all, you have to know what recursive means. What is it when I say a recursive method? What am I talking about there? Well, what's the definition of a recursive method? Go ahead.
It's a method that can call itself within.
Yep, so a method that is implemented in terms of itself, a method that calls itself from within itself. All right, so somewhere in your implementation, you should have been calling the method you were writing. That made it recursive, okay? So what we really want to do here, and I'll write a version of this, is you want to take in a stack, and as long as the stack is not empty, you want to pop the top of the stack, print it, and then and when you pop something off the stack is now smaller, right? And then call the method again with the updated stack. Keep doing that until the stack's empty. All right. Common problem on this one was if when we think about our linked data structures are collections of nodes, right? So typically when you get a value, you actually have to get the payload from a particular place. So when you pop off the top of the stack, okay, you need to get the payload of that value in order to do something with it. It's like a point or something like that. But common bad problems that people I ran into with stacks and linked lists, and this is one of the things that may have haunted you like through the whole exam. Either you didn't treat a stack as a stack. You either treat it as a linked list, or even worse, you treat it as an array, where you just had like bracket notation. Oh, the stack at bucket 3. You put the square brackets after that. So, understand that the reason we learn about stacks and linked lists, and we're going to start talking about queues, is because each of these provides a functionality that leads to certain kinds of problem solving. Okay, when we do the shunting yard algorithm, we're going to talk about it today. But when we actually, and then you'll implement it, and then I'll actually solve it. That uses both stacks and queues to solve the problem. And it's not difficult, okay? But you're having to work with these little machines, right? You have a machine that works like a stack and another machine that works like a queue. So when you use a stack, you're going to be doing push, pop, and peek stuff. When you're using a queue, you're going to be using DQ and NQ stuff. NQ means get in the end of the line. DQ means get out of the front of the line. All right, so you want to use these tools for what they were built for. Where a linked list is much more generic, right? Linked list is something that kind of is a jack of all trades, doesn't really lend itself to any specific kind of problem. All right, and I don't know if I left justified this yet, so let's go ahead and do that. All right, so this guy's just supposed to print the contents of a stack. So we might go ahead and say, so it's void, not going to return anything. We can call this guy display stack. And this guy will take a stack S as a parameter, perhaps. We go ahead and drag this guy down here. All right, so you might say if S dot, or if not S dot is empty. So that would be a reasonable assumption to be able to check to see if a stack is empty. If you didn't want to do that, you could say if S dot peak not equal to null, that would do something pretty similar. If I peek at the top of the stack and there is something there, that means it's not empty. Make sense? So you can assume there was an is empty function, or you can just check yourself. It doesn't matter. They do the same thing. So if we still have stuff on the stack, okay, then we're going to go ahead and we're going to do a system.out.println s.pop.getPayload, or something along those lines. So that'll print out the value that was just popped off the stack. Okay, so we'll pop a node off the stack, we'll get that node's payload and print it. Remember I said in the instructions you do not have to preserve the stack, so this guy's dead. Okay, the thing we just popped off is now gone. So after I've printed that guy, then I'm going to go ahead and call display stack again on the same stack. But that stack has been modified. It's one smaller than it used to. It contains one less thing than it used to because I've popped something off. You remember from question, 2? That pop means remove something from the stack. Well, return the top of the stack, removing it from the stack. All right, questions on that one? So the recursive aspect of this is this guy right here. And you could have said this dot if you wanted to decide this was in the context of a program or something. That's fine, whatever. Okay, so that's that one. Let's see. 6, write a method named index of that takes a linked list and an int for which to search. The method should return the index where that int is first found, or -1 if it is not present in the list. All right, so this is your traditional index of for a string, but we're implementing this for a linked list. All right, Sorry, I'm going to steal this structure here. Actually, I might as well steal the whole slide. Nailed it. All right. Actually, let's got this. Index of, and this guy took a linked list and an int val, something like that we're looking for. All right, and we're supposed to return the zero-based index of where val is first found in our linked list, or -1 if we never find it. Okay, so what were we testing here? We were testing your ability to traverse a linked list. So we're going to start at the beginning of the linked list. We're going to keep going all the way to the end of the linked list. Each time through, we're going to check the payload of the guy we're currently looking at. If it's equal to the value that we're dealing with, we'll return the position where we are. If it's not, we move on to the next one. If we run out of places to check, return -1. Okay, and you could have done this a couple of different ways. The easiest solution, and this might not be the easiest solution, but a reasonable solution, since we had advertised in class that we would keep track of the count of a loop, is just write a for loop that goes from I is 0 all the way up to the count, non-inclusive. So you do your little for int I is equal to 0, I is less than LL dot maybe get count, something like that. You know, however you wanted to write it. If you wanted to use bad programming and say that count was a public field, it's fine. You know, as long as your logic was pretty close. I plus plus. Okay, so now we know how many times we're going to go through. But now while we're going through, we need to be able to traverse through this linked list, right? So we're going to have to give ourselves a variable that's going to point to the current place in the list that we're looking at. So usually we call that with like cur node or something like that in class. So maybe we'll do node cur node is equal to LL dot, you can do head, or maybe you can do get 0, something like that. You know, however you wanted to assume that the linked list provided you access to the beginning of the list. All right. And you could also even go as far as to saying if index of is, now, I would have allowed this just because, you know, you're on a timed time thing and, you know, you don't necessarily think about all the little things. But because we're taking a linked list in as a parameter, this probably indicates that we are not inside of the linked list class. So this dot head likely doesn't exist here. But if you wrote that, that's fine. I was looking for the line here that kind of says, give yourself a pointer to the beginning of the list. Okay? Because you don't want to change head regardless of where you retrieved it from. Okay? So cur node is going to be the beginning of our list. Then we'll go ahead and we're going to spin through every element of the list. First thing we'll ask is if cur node's payload is equal to val, and we know that cur node will be something in here, right? And we know it's going to actually be something in here, otherwise we wouldn't have gotten inside of the for loop, because for loops are pre-check loops. And we know also at the same time here that if we are still kicking down here, we can go ahead and return a -1. If I've checked everywhere and I didn't find it, I'm supposed to return a -1. That's what the question said to do, right? So inside here, we're going to ask the question, if cur node dot get payload or something like that is equal to val, then we're going to go ahead and return the current value of I. Uncapitalized. And you could put this in an else if you wanted to, but it doesn't have to be because return makes a method immediately end. So you're not still kicking on this line unless you didn't return. In which case we would say cur node is equal to cur node dot get next node. Something along those lines. Make sense? Traverse your list, look for the value you're searching for, which is this dude up here. If you find him, return where you found him. First time, the first occurrence of him. If you didn't find him, traverse to the next node in the list, spin back up. We know we're still kicking because this for loop happens to go through the exact number of elements in the list. If you survive this whole for loop and never return a value, that means you didn't find it, return -1. Alternatively, you could have made your loop based on while cur node has an x node, that type of thing. But then you would have had to you would have had to provided yourself with a counter to keep track of where you were in the list, that type of thing. Same logic, just if you used the loop that didn't give you a number, you had to provide your own number. All right, questions on that one? All right, what number was that? 6. All right, 7, reverse list. Takes a linked list as a parameter and returns a new linked list as the original in reverse. Oh, sorry. Copy and pasting is your enemy. This guy should have a return type of int for the index of. This guy is going to have a return type of linked list. And we're going to reverse whatever linked list was passed in. So very first thing we're going to do is we're going to build a brand new linked list. So there's our new linked list. Now we need to traverse our old linked list. Okay, you could traverse it the exact same way we just did in the previous question. So we can say node cur node is equal to ll dot, get it bucket 0 if you want, or get head, or just head, whatever. Okay, so get the front of the list. Then you can do the same for loop. You want to do it on count, or you can just do it on while cur node has an x node. Doesn't matter, but let's go ahead and do it like we did the previous one. Killing me here. All right. Now, what we want to do is we're trying to reverse the original list. So we're going to keep adding the current guy we're looking at in LL to the front of our new list. Okay. Just always add front, and now you're going to build it in reverse. So answer.add front ll.get I. And then at the end, return answer. Okay, we're returning a brand new linked list that is our original one in reverse. All right. Some people here at the end, they did something like LL equals answer. If you did everything else right, that was okay. But you're supposed to return a new one. All right. So build a empty linked list, spin through your existing linked list. For each value from your existing linked list, add it to the front of your new one. So you'll end up building it in reverse because you're always adding onto the front of it. All right. Then in the end, return the answer. Questions on that one? Oh, I named it wrong. Supposed to call reverse list. Minus 10 points right there. Didn't you miss 1,000 on one of your questions?
Yeah, I missed 1,000 on number 6.
That's a lot of points, dude.
We ended up reducing it to 1.
All right. I'm on. What am I on? 8? Write a method named remove at index that takes a stack and a 0-based index as a parameter, and it should remove the element at that index in the stack, leaving the rest of the stack intact. For this problem, position 0 in the stack is the top of the stack. Okay. So this is a push-pop exercise, right? Oh, did I paste it already? Nope. Okay. This guy doesn't have to return anything because stacks are manipulated in memory. What's it called? Remove an index. And this guy's going to take a stack and an int index that we want to remove. All right. So what we need to do is we need to pop from the current stack all the elements up to, but not including that index. But we need to have a place to put them, because if we just pop them, they're lost. All right, so we're going to give ourselves a nice little temp stack. So stack temp is equal to new stack. All right, then we'll say for int I is equal to 0. I is less than, now, you know, if the value we want to omit is bucket 3. Okay, in there, we need to get everything up to but not including bucket 3. Does that make sense? So I is less than index I plus plus. And we'll go ahead and say temp dot push s dot pop. All right. So now what we've done is we've copied onto temp. We've revealed the guy we want to remove at the top of S, preserving all the other guys over here in temp. All right. So now we want to remove the guy that we want to remove, and we just say s dot pop. We don't need to catch him anywhere, just out the window, gone. All right. Then we need to go ahead and push everything from temp back on to put it back onto S, and then we're done. All right. So we could ask temp how many things are in there, but typically we might do something like while temp dot peak peel is not equal to null. I hate this keyboard. Program's so slow on this thing. Well, temp.peak is not equal to null. That means there's still stuff in temp. We'll go ahead and say s.push temp dot pop. Killing me. It's going to make me lose the hackathon. I'll tell you what. That's what this is going to do. Temp.peak not equal to null. S.push temp.pop. So get the stuff off of temp, put it back onto S, stacking it on top of what we previously removed. Soon as we're out of stuff, we're done. We have nothing to return because that stack exists in memory, right? S was a pointer to the actual stack up here. So now we've manipulated that stack by taking everything before the guy we want to remove off, pop that guy off, put all this crap back on. Questions on that one? It's kind of a fun exam, actually. I like this one. What do the following methods do? First one, do something. We create a new stack called temp stack. And while the stack that came in is not empty, so while there's still crap on the stack, notice that the first two lines of this, we say s.peak. We are not removing that value from the stack S, but we are getting the value. So what I'm doing is I am pushing onto temp stack the top of S twice. And then that third line there, s.pop, is when I actually remove that element from S. That make sense? So every element in S is being duplicated 2 times inside of temp stack. So that's one thing that's happening. In the end, I'm returning temp stack. Now, temp stack, it was okay if you just said every item was repeated twice. I gave you credit. But technically, temp stack is also the reverse of S. So it's all the contents of S duplicated twice in reverse. That's what this dude ultimately does. That makes sense? And the important thing there, and that's why I was referencing number 2 earlier, that you needed to understand what those 3 functions were: the peek, the pop, and the push. So, understand that peek gives you the top of the stack without actually removing it. That's an important thing there. Okay. Number 10. One person in the entire class got this one right. And it was Emma. Okay. And I gave her bonus points for it because she made a stupid mistake on the previous one. So, other people did not lose points for a wrong answer on this one. So what this one's really testing is your understanding of linked data structures. So at a glance, what does this guy do? It creates a new blank linked list, right? Called answer. Then it grabs one node from position pause in LL. And then, now notice my little comment there next to node cur node equals ll.getNode. It says return a node without removing or disconnecting it. So this gives me position pause in my from LL, and I'm storing it inside of cur node. Then I just add that cur node to my blank linked list. So many of you said, "Oh, this returns a new linked list with position pause from LL as the sole member of it." Anything else? Now that I've kind of elaborated a couple of the things here, anybody else want to, besides Emma, want to interject maybe what I was actually looking for there? If I were to print out answer after this, what would print out? You're going down a decent path, but give me a little bit, well, you might be going down a decent path, or you might just be saying it in a really bad way. Tell me more.
Well, it's because you never disconnected it, so that node is still linked to the next node in the list that you pulled it from.
Yeah, so if I were to print out answer after this, it's gonna print out whatever was at position pause in LL, but it's also going to print out all the other stuff that came after that. Because that stuff's still connected. When I removed, well, I didn't remove it. When I got this node from LL, so I have this guy. There's still stuff connected to him, but when I print, I'm probably not going backwards. But he's connected to other things. And I just put him into this list, so he had another pointer. So I still have a list of stuff, even though it seemed like it was only a one list. Does that make sense? All right. So, is that the whole exam? That's the whole exam. Questions, comments, concerns, bribes?
So it's going to be copied and now to the front of the linked list, right?
Well, yeah, it's going to, answer is going to contain what seems to be one node, position pause. But it actually has everything that came after that guy with it, because it's still connected to pause. Okay. Huh? You think? Well, I didn't take points off. Yeah. So a lot of people got no points off. Only one person got extra points added. That was Emma. She answered the question correctly.
Yeah.
Not this made up crap.
I say the method copied now to the front of the linked list and based on the parameter pop.
Yeah, that's what everybody else said. It's the same wrong answer. I mean, it's the same half wrong answer. I mean, it's true. That's what it does. But you didn't show me that you understood that a bunch of other crap was drug into the locker with them. All right. But does that make sense to everybody now? That because it didn't get disconnected, these are all just pointers, right? And if I take this pointer and I give another guy pointing to him, there's still crap hanging off of him. It didn't go anywhere. All right. All right, so let's talk about, and if you have any questions about, any specific grading on your exams or anything, just come up after class and I'll tell you why I took points off, or if you deserve points back, I'll give you points back, or if you think I gave you too many points for any questions, let me know that as well. You want to be honest, right? So if I gave you full credit for something, you said, I really deserved half off for this.
I want my negative 1,000.
Like, this score you added wrong. That would calculate really horribly. All right, so let me know that though today, right after class. So if you deserve any points back, I'll add them into the grade book because I'll be putting in midterm grades later today. We're supposed to, so you can check to see how crappy you're doing. But like I already said, I think everybody in here should not drop. Some of you should kick it into gear a little bit, but I think everybody in here is at a reasonable, you're doing okay, at least. But I'll put those midterm grades in. I want them to be accurate, so if you deserve any points back. Also, double check Blackboard and make sure that any extra credit you deserved was accurately represented there, or that kind of stuff. I think I have everything graded in the grade book now, so nobody should be missing anything that they turned in. Right? If you didn't turn it in, you got a 0. That is accurate. That's an accurate assessment for what you earned for that. Okay. So let's talk about cues for a few minutes. So just kind of giving you a little foreshadowing where we're going the second 8 weeks. We're going to start off with cues, and we're going to write this algorithm. What do I call the algorithm? Shunting yard. The shunting yard. That just sounds scary, doesn't it? The shunting yard algorithm. Yeah, that's why I picked it. I mean, I went on to Wikipedia, and they have a little random button at the top, and you can put in algorithms and say, I feel lucky. Google used to have that. You know that? And then it brings up just random algorithms. I just picked the top one. They probably can do this. I haven't even looked at it. I don't know what it is. No clue. So I look forward to solving it on Thursday. Should be amazing. Okay. So when we talk about cues, I was about to spell that right? Nailed it. So kind of where we're going the rest of the semester, this final 8 weeks. So we're going to kind of deal with cues relatively quickly. And I have one assignment on it because this one assignment is kind of maybe let's call it the culmination of our linear linked data structures. All right, so in this, so I guess I'm showing my hand here a little bit, literally. I do know what the shunting yard algorithm is. So in that, you're going to have to use linked lists. You have to use queues and stacks, okay, which are both just mini versions of linked lists. Okay, I mean, which is easier, the full-fledged linked list that has all the little bells and whistles, or a stack? A stack is really a simple linked list, isn't it? Because you only have to have a couple of functions to let you do this stuff. And they're the easy ones, right? Add front, remove front. Pfft, those were the easy ones. All right? It's the whole remove an index or add an index. Those are the ones that sucked. We had to draw the pictures and the lines and all that stuff. Okay, so we're going to introduce cues really quickly here. And it's still mostly the easy ones, except you have to remove front and you have to add end. Not the end of the world, right? Dr. Banouche, Q. I've gotten funnier over break, I think. Gary, you don't think so?
Must have been about this.
Oh my gosh, the ribs were so good. I would move there just for the barbecue. It was legit. What's even funnier is me sitting there eating these massive racks of ribs in front of 2 Jews. And making them pay for it. It was great. It was great. My dad could eat beef brisket though. But he always complained it was too dry. My mom would get like a salad or something. Well, actually, she had ribs a couple times too. My mom is a terrible Jew. It's like, oh, that pork looks good. Totally true. All this is true story. I made them pay for every meal and my gas in my car. And I got these new shoes. Look at these. Mom bought me those. I had a good trip. All expense paid. All right, I just had to schlep them everywhere. See, that's a Jewish word, right? Schlep. Drive them around. All right, so we're going to be doing, we're going to finish up our linear linked data structures. Then we're going to start moving into non-linear linked data structures. So these are things that are going to be like trees, graphs. Those are going to be the two, let's call the two highlights. But intermixed in there, we're going to do we're going to implement several algorithms that some of them directly relate to those, some of them indirectly relate to them. But what they're going to attempt to do is give you a picture into maybe the larger world of algorithms. Because the way I like to look at 300 is it's a data structures course, but it's also an algorithms course. All right, so yeah, we want to introduce these common old school data structures, binary trees, search trees. The one you're going to hate is something called an AVL tree. Anybody in here ever heard of an AVL tree? Oh, yeah. There's kind of two competitors. There's AVL trees, and then there's something called red-black trees. They kind of are a similar spin on the same thing, but you have this idea when you think about a tree data structure, which we'll be getting into next week maybe or something like that. It's nonlinear. So you have kind of a root node, and then so think about a tree, right? In real life, you go outside, you look at a tree, flip it upside down. That's a tree data structure. Okay? So, you have, actually, no, you can think of it right side up. So you go to the very top, there's a tippy top to the tree, right? That's a Trump quote. Isn't it? Tippy top. No, you just said it a couple days ago. When you say something about nuclear weapons, Russia's nuclear weapons are tippy top, and we need better ones.
That would be the ones that you picked out.
It sounded funny to me. Well, I get all my news through like YouTube funny videos. Yeah, so I only get the highlights. All right, so you have your kind of a root node, and then you have things coming off that root node, and then things coming off that guy, and so on and so forth. And that's for a binary tree where the maximum number of children might be 2. Well, then you can have an n-ary tree where every node might have 50 nodes coming off it. So if you think about a binary tree, it might look like if you go outside and you look at a tree, and it looks like very very organized. Not too many branches, but just enough, right? It's kind of a binary tree. Then you have one of those trees that just looks like it's just a wall of leaves. Those are n-ary trees where there's no rhyme or reason of what's going on in there. And then we're going to look at searching algorithms for them. But AVL trees and red-black trees, they're what are called self-balancing trees. Okay, so let's say you walked outside and you saw you have a tree, and I say each leaf on that tree has a little number on it. Okay, each leaf on the tree has a number on it. I want you to find a number. Now, if I tell you that there's some sort of let's not go too deep into that, but you're going to find a number on this. Well, if you go outside and you find a tree that has one side is half the size of the other side, so you have one side of the tree that has tons and tons of leaves on it, and the other side of the tree has half that on it. You might start searching on the wrong half, right? Okay, so you're kind of coin flipping on whether or not you're assuming the leaf you're looking for is there. You're kind of flipping a coin as to whether or not you're going to be spending a lot of extra time or you're optimizing your time. So the idea of self-balancing trees is at all points in time after you add a new leaf to the tree. Okay, because that's the way God works. He goes out and when there's a tree, he just puts a new leaf right there and just hopes nobody notices. And eventually that's how we go back to the summer, right? Or spring. The trees get leaves back in the spring, right? That's what happened right now. Yeah, I mean, have leaves, don't they? If you sat there and you looked at each of those trees each day, you'd notice they call this. God's little sense of humor there is what it is. Okay, so in any case, every single time a new leaf is put onto the tree self-balances itself to kind of keep itself within one level of each side. All right, so when you go out beginning of the summer, once the trees have gotten all their leaves back, are they back by the beginning of the summer? When are they back? Summer. Okay, so that's when I really need to make sure I hit my tee shots around the tree. So right now you can hit them right through them. You got an 85% chance of not hitting anything. But you know, the idea is that if you were to go out and search a balanced tree, it didn't really matter which side you started your search on because they're both about equally bad. Does that make sense? But that self-balancing algorithm, the algorithm of rotating this tree to keep it in balance, sucks. Okay, and you know how sometimes I say something is like really hard, and then I'm kind of kidding. Well, you might not think I'm kidding actually, but kind of notice that I am kidding once I actually do it. No, this one sucks. AVL self-balancing algorithm just sucks. It's terrible. So we shouldn't do it, right?
No, just do it.
Yeah, we should do it because we're warriors, right? You know, just because it hurts doesn't mean we shouldn't persevere.
Just do it.
Just do it. That's right. All right. So that's kind of what's coming, and then mixed in there, we're going to have some other interesting algorithms. We're going to be looking at. Do I remember the name of it? Maybe not. We'll be looking at a sparse tree algorithm. Or sparse matrix algorithm that how do you represent really large data sets, like things like maps and things like that. So for example, let's say that you wanted to store the information, so we'll just pick a relatively small data set inside of a large area. So let's take the United States, large area, right? And how many airports are there in the United States? A lot, but far, 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 far fewer than the size of the United States if we picked every little GPS coordinate. Okay, and let's just even take it down a step further and say major airports. So now we have a significantly smaller. So let's say we have something like, I don't know, 30 major airports in the United States, things that we can roughly say are major airports. And these guys are spread all out, right? Now, what you might do is you might decide, okay, well, I'm going to take the entire United States, I'm going to break it into a grid, right? And we're going to plot where each of those major airports are, each of those 30 major airports are in the entire grid. So now you have this giant grid, right? With tons and tons and tons and tons and tons of buckets, if you think about it like an array, okay, a two-dimensional array. And in there, you actually are only holding 30 pieces of data. Does that make sense? That's not efficient, is it? If you were to compress all this, so now you're storing all the places where there are not airports, okay, and then the 30 places where there are. That's a lot of data that didn't need to be stored that way. So really, this is an example of a compression algorithm, okay? So how do we store that map of the major airports in the United States in a small footprint such that it could be rebuilt? You know, when you unzip a file, you double click on it and it unzips and gives you all the magic back, okay? You could rebuild that map if you needed it, but if you needed to hand somebody that map, you could hand it to them in a smaller package. Does that make sense? So we'll be looking at a compression algorithm. I forgot the name of that one. Well, maybe we'll luck out. It'll pop up on my random Wikipedia search again. We can only hope. All right, queues. Queues have two, built-in functions. Let's say DQ. Oh man, ice cream! I love ice cream. And NQ. Ooh, Q is kind of a fun thing to type. It's like Mississippi. Okay, so DQ and NQ. DQ says, well, here, for starters, This is a line. Ask Dr. Manouche. All right. You said he mentions me in class pretty often, so now I got to start mentioning him, right? Does he still do that?
A little bit.
Oh, so I'm not on his hit list anymore. Now I'm offended. Okay. So all a queue is a line. We're emulating a line at McDonald's, a line, whatever. Lines all over the place, right? So when we solve problems in real life, we see lines. And it's human nature to go and get into a line. Okay, so DQ says leave the line. And when we leave the line, we exit from the front of the line. So when you're next in line at McDonald's, you DQ the line and you walk up to the register and order your Blizzard, because now we're talking about DQ. Our line is that Dairy Queen. Okay? Line is that Dairy Queen. You leave the line, you order your Blizzard. It's not on my diet. It's the worst thing for me, for my low-carb diet. Blizzards are pure carbs. Pure carbs. It's just made of sugar, those things. It's so good. All right, so DQ, leave the line. Exit from the front of the line. So if you want to think about this from a linked list perspective, because this is still a linear linked data structure. It's built on a linked list, just like stacks work. This is remove front. Easy, right? This is the same thing as pop. All right, NQ. Get in the line. Enter the line from the back. This is add end. See, Alexis is always having to look up so you can see the bottom of the screen. We need stadium seating. Oh, he's too tall. That's not your fault. She's too short. You remember that. People have been telling me I'm too tall my whole life. See, my wife complains because at my house, if you've met my wife, she's little. My wife's like 5'4", like, I don't know, 110 pounds. She's little. I don't even have to buy an extra seat on an airplane. Just put her in my carry-on. After takeoff, I can... It's a true story. I tried it once. So she likes putting things down in lower cabinets. Okay, well, my height, I put stuff above the cabinets in the kitchen. On top of the cabinet. She didn't like that. She says it makes it look cluttered. That's a wasted space up there, isn't it? Why don't they have cabinets on top of the cabinets? Like go all the way up to the ceiling. Well, they say, people can't reach them. I can reach them. Dumb.
Step ladders.
So I don't need a step ladder. Oh, she needs a step ladder. Oh, you're like my wife's height. How tall are you?
5'5", 5'6".
Oh, no, you're like my sister-in-law's height. Pathetic. But you probably like those low cabinets. You can get to them real easy. No, I sometimes, if I got to really look for stuff in there, I just sit down on the floor. I'm just rooting around in there, and then I have to find a chair to crawl over to get back up.
There was some stuff in your garage, but I was like, Schumacher.
Yeah, he's tall. He's a little shorter than me, but it's like 6'3" or something like that. Yeah, you should really be asking, why does he know so much stuff about my garage? I was in your garage that one time, and he's been in my basement too. Why have you spent so much time in my garage?
Well,
and you've been in the basement. You've seen the rope system.
I'm still confused.
The whole room is like, this is crossing some boundaries. All right, so queues are just an implementation of a line. Now, how would you implement add end? We've done it before, right? Or I'm sorry, how would you implement NQ? We've done it. We've written our generic linked list to add something to the end of the list, correct? And what do? We traverse our list. We go to the beginning. We walk all the way to the end until we finally get to a node whose next node is null, and we park ourselves right there. Okay? Is that a problem? Now, if we think about this in real life, That would be kind of weird, right? So you walk into McDonald's. I can sometimes pull this off. I can just kind of act like a vagrant. Okay, and you're just a fat guy. You walk up to them. Okay, but you start at the front of the line. Say, "Are you the end of the line?" Nope. Go to the next. Are you the end of the line? Just keep going back until the line starts parting because they don't want to. I don't want to talk to this guy. Okay. In real life, that doesn't make a lot of sense, and it's inefficient. Correct? Okay, so if I start at the front of the line, I start traversing the line all the way to the back until I finally find my spot. Okay, that would be creepy. So what could we do instead? Go ahead. Keep track of the end of the line. And this was brought up earlier in the semester, right? Somebody mentioned, I think even the reading talked about doubling linked lists. And I kind of said, we didn't really have a use for them at this point in time. And actually, we don't even have a full use for doubling linked lists yet. All we have is a use of one more pointer that we might keep track of in our linked list. And what's that pointer? That pointer is tail. So now we're going to keep track of two things, the head and the tail of the list. Now at the beginning, with the empty list, head and tail are both null. When we add something to the list, and we have a one list, head and tail both point to the one thing. But as things start getting added to the front, tail remains pointed at the last node in the list. Head moves along with things being added to the front. Okay? So at all points in time, tail will always just point to the very last node in the list, which gives us convenient access to the end of the line, the end of the list. We don't have to start at the beginning and traverse to the end. We could just say, I'm going to go to tail. I'm going to add something right after that, and then I'll make tail point to me because I'm the new end. So with tail, one more variable involved. Okay, we don't have to do the whole doubling linked list thing where we have nodes knowing about previous nodes. We don't need that functionality for queues, right? Unless we start doing line cutting. Okay, which I'll talk about here in a second. Okay, but for our cues that we're going to need for the homework assignment, you don't need that. All right, you just need to know the end of the line. Okay, I'm supposed to get in the end of the line. I go to the end. Now I'm the end. Tail points to me. Okay. I'm exiting from the front of the line. Who's exiting? Go to head. He exits. Head now points to the dude that was behind him. Make sense? His next node. All right, so cues are really simple. All right, and you can even implement them without tail. Just takes in the real life version, it's a little creepy. You're kind of running to the back of the line from the front, but computers are fast. Who cares? So you can just use your existing linked list implementation if you wanted, and create a couple of synonym functions. Right? DQ is remove front. NQ is add end. You can just even have them call those functions, right? And now that's a queue. Problem solved. Okay, now notice that I'm purposely avoiding talking about shunting yard right now, because what I'm going to do is we need to be able to, you get in the real world and you start working for places, you need to be able to look at an algorithm and implement that algorithm, right? So I'm going to give you the Wikipedia page for it is actually pretty good. But I'm going to have you implement the algorithm as an Android app based on the Wikipedia page. All right. So instead of me spoon feeding it to you, you're going to have to implement it off of documentation. Some of you will find that challenging, some of you won't, but we'll take care of it on Thursday. A heap. How many of you have heard of heap as related to technology? A couple of you've had the operating system class, haven't you? Didn't talk about heaps in there at all?
Not that I recall.
Well, a lot of times a heap kind of gets thrown out there, kind of like you maybe talked about stacks at some point in the operating system when you were talking about CPUs. So sometimes heap falls into that same kind of, you have a stack where, where certain things get stored for implementing recursion, and you have heaps where maybe something else gets stored. You never really talk about what a heap is. Okay, so I'm going to go ahead and give us a quick definition of a heap to kind of fill in that final gap of when do we need that doubling linked list. All right, so a heap is sometimes called a priority queue. Okay? Remember that whole rule, no cutsies? Heaps allow cutsies. Okay? So with a priority queue, when somebody gets in the back of the line, if they're more important than the people in front of them, they can cut the line. Right? We see this all the time at airports. You have the blue pass people or what, a couple different lines you have to get into. So you have you sort yourself, like whether you're like the steerage versus like more important people. I'm always in the steerage because I don't want to pay extra because I get my free extra seat anyways for being fat. Love Southwest. Awesome. So, in any case, a heap is just a priority queue. It works like a queue. We still have NQ and we have DQ. Okay, but when people NQ, they potentially can bump up the line. All right, to position themselves in their order of importance. Disney World has implemented a heap data structure now, right? When you go to Disney, you can pay for your normal ticket or you can pay for the speed pass thing that lets you cut the line, right? Isn't that how it works? Fast pass? So you know all about this. Yeah, see, I don't fit in any of the rides, so I don't. I once sunk the boat on It's a Small World. We started taking on water. They put me on my own boat. Yeah, dead serious. dead serious. That was bigger then. That was when I was over 400. So they put my wife and I. This is actually when we got engaged. It was the trip when we got engaged at Disney World in front of Cinderella's castle. It was right after I broke my back, so I'm wearing this. I have a live picture of it my grandpa took. So I'm wearing this huge back brace, and I actually got down on a knee and couldn't get back up. I had spectators come and give me up. It was pretty pathetic, but yeah. So I got on the back of the boat of It's a Small World, and started taking on butt water. It was pouring in the back of the boat, so they put us in our own boat, and they centrally sat us. So the weight would be distributed. That was funny. All right, so in any case, all a heap is a priority queue. You get in line, and sometimes you're able to bump up the line. And because you're allowed to bump up the line, now you have this idea of it might benefit us to know who the previous node is, right? So we could ask the guy, hey, am I more important than you? Yep, get out of the way. That type of thing. Make sense? That's what a heap is. We're not going to talk more about it right now, but that's what a heap is. So let's shunting yard algorithm right here. All right, so, and I know we're out of time, but I'll just take 30 seconds to kind of show you this. So notice we have 3 different things here. Well, really, we have 2 different things we're working with. We have an input queue, and we have an operator stack. So remember way back when we did that process expression function, was it probably a 200 or 250? Probably 250 for you guys. We do it in 200 now with the Python stuff, but where you had to take in a string that was like a math formula from left to right, 123 plus 7 minus 4. Remember that guy? Okay. And I said you have to work, you can only has to work left to right. You don't have to take order of operation into consideration. What if you did need to take order of operation into consideration? So what the shunting yard algorithm is, it's a conversion from standard notation to reverse Polish notation. So what you get in the end, if you look down here, is you end up having a stack of operators that always go in based on which is the higher priority. So multiplication is more important than addition and that kind of stuff. Okay, so I'll put the link up to this algorithm. All right, now for you, it's up to you. You can choose whether you want to implement this in a normal Eclipse project or you want to implement this as an Android application. Either one is fine. Don't get fancy with the interface. In fact, if you wanted to, you can implement it as an Android application, but have no interface. Just use system.out.println initially, and then we'll add an interface to it next class. Okay? But the idea is what you'll take in is you're going to take in a string that's a formula, 123 minus 8 times 2, that kind of stuff. And then you're going to tokenize that, break it into its individual pieces, and add those to a queue. Then you're gonna DQ off that queue and decide, where does this guy go? Is he an operator? If so, he gets pushed onto the operator stack. If he's a number, then I need to do something with him, and that's off. We use the operator stack to decide what we do. Okay, so they give you a lot of examples of how this works and stuff like that in here. The one thing I'll say, if I scroll down here, they give you order of operation for these different things. You do not have to handle powers. So just multiplication, division, addition, and subtraction. Just our 4 standard mathematical things to get a feel for this. That makes sense? So you choose your interface. All right, so I'll put this up on Slack, then I'll put the thing up in there, but you're gonna implement a queue, which you should pretty much already have implemented with your linked list. And then you're gonna use your stacks as well to do the shunting yard algorithm for Thursday. Sound good? All right. Don't forget, today is student, faculty, staff Bible study. Just go down to the cafeteria, you sign in, you get a free lunch. Take it down to the terrace room and you eat with us. A bunch of us sit in the cafeteria for a half hour first because it doesn't start till noon.